Hello everyone and welcome to Machine Learning with Pats. If you're passionate about numerical problem solving and exploring the applications of principal component analysis, you're in the right place. Whether you're a seasoned professional or just diving into this fascinating world, we've got something exciting for you. Today our focus is on PCA applications across 8 mechanical domains. I will talk about how principal component analysis plays a pivotal role in various aspects of mechanical engineering. So, get your notepads and calculators to explore these problems. To give our exploration a practical touch, we'll identify common problem statements that PCA helps address. Now, the real excitement begins as we narrow down our focus to 8 mechanical domains such as structural engineering, fluid dynamics, automotive engineering, aerodynamics, thermodynamics, material science, robotics, and energy systems. Let's start with structural engineering. It plays a pivotal role in ensuring the safety and efficiency of large-scale structures, especially in the realm of renewable energy. We will examine its impact on the design and performance of wind turbines. Let's explore the material properties, applied loads, geometry, and stiffness on structural behavior. Moving on to the industry relevance, let's understand relationship between material properties, applied loads, geometry, and structural stiffness. Why is this understanding crucial? Because it forms the bedrock of designing resilient wind turbines. This knowledge ensures these structures can endure the demanding conditions of wind energy farms, ultimately enhancing the reliability and efficiency of renewable energy production. When applied to wind turbines, material properties become crucial for withstanding the dynamic forces imposed by wind loads. Applied loads, in this context, include the fluctuating wind forces that influence the stress distribution across the turbine components. The geometric design influences load distribution, ensuring optimal energy capture and structural integrity. Moreover, structural stiffness is paramount for stability, ensuring the turbine can endure varying wind conditions without compromising its functionality. Utilizing PCA, we seek to uncover the primary factors dictating the performance of these large wind energy structures. So what is our problem statement here? This investigation seeks to answer the following question. How do material yield strength, applied wind loads, geometric design, and structural stiffness contribute to the diverse structural behaviors observed in large-scale wind turbines? Through the application of principal component analysis, PCA, on this dataset, we aim to identify the primary factors influencing the structural performance of these turbines. These insights are crucial for enhancing the design, reliability, and efficiency of wind energy structures, ultimately contributing to the advancement of sustainable and renewable energy solutions. Look at the table here. Turbine ID represents the unique identifier for each wind turbine. Yield strength denote the material strength of the turbine components. Applied loads represent the wind forces exerted on the turbine. Blade length is the length of turbine blades, which affects the area covered by the blades and the potential energy captured from the wind. Structural stiffness quantifies the structural stability of the turbine components. Now we will discuss role of PCA in fluid dynamics. Fluid dynamics, the study of fluid behavior in motion, delves into the nuanced dynamics of 4 key parameters: inlet velocity, fluid density, pipe diameter, and friction factor. These elements are pivotal in unraveling the intricacies of fluid flow within dynamic systems. It finds paramount significance in HVAC systems. Inlet velocity regulates the airspeed for optimal circulation. Fluid density governs mass flow rates, impacting precise temperature control. Pipe diameter influences airflow resistance, directly affecting energy efficiency. Friction factor contributes to energy losses, influencing overall HVAC system performance. So what is industry relevance? First is efficiency. Optimizing these parameters ensures efficient air distribution. Next is comfort. Proper fluid dynamics contributes to an ideal indoor climate. Third is energy conservation, where understanding and controlling these aids in energy-efficient HVAC system operation. Let's look at its impact. In residential area, it enhances home comfort with precise temperature control. While in commercial applications, it ensures optimal air quality and energy efficiency in office spaces. In an industrial domain, it is critical for maintaining controlled environments in manufacturing and production facilities. As we dig into our dataset, the challenge is clear. How do these technically intricate parameters, inlet velocity, fluid density, pipe diameter, and friction factor, intricately influence fluid flow characteristics within HVAC systems? Our mission is to dissect and analyze, unveiling insights that have implications for elevating HVAC system design and performance to new heights of efficiency and sustainability. Apply PCA. This dataset includes samples with corresponding values for inlet velocity, fluid density, pipe diameter, and friction factor. Look at the data in the table. Each sample represents a specific scenario within an HVAC system. Analyzing this dataset through principal component analysis, PCA, will uncover patterns and relationships. This will provide insights into the dominant factors influencing fluid flow characteristics. Our third application is automobile engineering. Let's find relationships between engine temperature, vehicle speed, fuel injection rate, and tire friction. Engine temperature plays a pivotal role in determining the efficiency and overall performance of the engine. An optimal temperature ensures combustion, contributing to fuel efficiency and reduced emissions. Beyond its obvious influence on travel time, vehicle speed significantly affects aerodynamics. Higher speeds introduce increased air resistance, impacting fuel consumption and requiring careful engineering to balance speed and efficiency. Fuel injection is a critical aspect of the combustion process. Controlling the injection rate directly influences the efficiency of fuel combustion, affecting both power output and fuel economy. Tire friction is the bedrock of vehicle dynamics. Proper friction ensures traction, stability, and efficient braking. It's a key factor in optimizing safety and performance. As far as industry relevance is concerned, the optimization of fuel injection rates contributes directly to fuel efficiency, a cornerstone in designing eco-friendly and cost-effective vehicles. Managing engine temperature ensures the combustion process is calibrated for maximum energy extraction from the fuel. Friction, when controlled effectively, enhances traction and stability, crucial for both safety and performance. Adjusting vehicle speed not only impacts fuel consumption but also influences aerodynamics, an essential consideration for achieving an optimal balance between speed and efficiency. Within automotive engineering, our task is to discern how engine temperature, vehicle speed, fuel injection rate, and tire friction collectively influence vehicle efficiency and performance. Employing principal component analysis, PCA, on the dataset, we aim to unveil intricate insights guiding automobile engineering toward heightened precision and efficiency. Look at the dataset in the table. Engine temperature affects optimal combustion. Precise control ensures efficient combustion, influencing fuel efficiency, emissions control, and overall engine performance. Vehicle speed has aerodynamic influence. Higher speeds introduce increased air resistance, necessitating strategic engineering to balance velocity with fuel efficiency in system dynamics. Fuel injection rate affects combustion efficiency. It is crucial for precise combustion, influencing power output, throttle response, ultimately impacting fuel economy. Tire friction plays an important role in vehicle dynamics. Effective management enhances traction, stability, and efficient braking, directly influencing both safety and overall vehicle performance. Our fourth application is aerodynamics. In the domain of aerodynamics, where we explore how the way planes fly is influenced by things like how fast they go, the shape of their wings, the air around them, and the lift coefficient. We're zooming in on commercial jet aircraft, those huge planes we see in the sky, to uncover the secrets behind their smooth flight. This matters because it's not just about planes, it's about making sure everyone gets where they need to go safely, without using too much fuel, and being mindful of our planet. Imagine we're looking through a magnifying glass at big airplanes. We want to know how things like how fast they go, the shape of their wings, and the air around them all team up to make them fly so well. It's like discovering the secrets that keep them soaring through the sky. Let's understand these terms. Airspeed affects dynamic pressure. The relentless push against the aircraft's surfaces due to varying airspeeds dictates dynamic pressure, influencing takeoff, cruising, and landing phases. Wing geometry affects lift and drag. The carefully designed wing geometry determines the balance between lift, enabling flight, and drag, a force to overcome during forward motion. Air density is responsible for lift forces. Air density at different altitudes significantly impacts lift forces, crucial for achieving and maintaining desired flight levels. Lift coefficient affects aerodynamic efficiency. The lift coefficient serves as a measure of the aerodynamic efficiency of the wings, guiding engineers in optimizing design for fuel efficiency and stability. What is the industry relevance? The first is according to efficient fuel consumption. It is important to understand aerodynamics to optimize aircraft design for reduced drag, enhancing fuel efficiency and minimizing operational costs for airlines. Next is safety enhancement. Precise knowledge of airspeed, wing geometry, air density, and lift coefficient contributes to safer flight operations, reducing risks and ensuring passenger safety. Third is environmental impact mitigation. Aerodynamic insights aid in designing aircraft with lower emissions, aligning with global efforts to minimize the environmental footprint of air travel. Last is innovative design strategies. Industry leaders leverage aerodynamic principles to innovate and optimize aircraft design, fostering technological advancements and staying competitive in the aviation market. In the context of commercial jet aircraft, the relationships among key aerodynamic parameters, airspeed, wing geometry, air density, and lift coefficient to be found out. How do these factors collectively shape the aerodynamic behavior of commercial jets, influencing efficiency, safety, and environment impact? So let's see the dataset in the table. Sample represents different instances or observations. In this case, each row corresponds to a specific scenario or test case. Airspeed, m/s, indicates the speed of the air around the object, measured in meters per second. Wing geometry describes the configuration or shape of the wings of the object, often specified by an angle in degrees. Air density, kg/m superscript 3, represents the density of the air through which the object is moving, measured in kilograms per cubic meter. Lift coefficient refers to a dimensionless coefficient that characterizes the lift generated by the object. It's a key parameter in aerodynamics. Our fifth application is thermodynamics. In thermodynamics, we explore the relationships between temperature, pressure, volume, and specific heat. Temperature influences energy transfer, pressure affects work done, volume plays a role in gas behavior, and specific heat determines heat capacity. PCA will help us identify the main factors affecting thermodynamic processes. Optimizing thermodynamic processes is crucial in energy production, refrigeration, and various industrial applications. So consider the dataset given in the table and answer how do temperature, pressure, volume, and specific heat contribute to variations in thermodynamic behavior? Our next application is material science. In material science, we explore the impact of material hardness, temperature, stress, and strain. Material hardness influences resistance to deformation, temperature affects material properties, stress impacts material strength, and strain deformation. PCA will help us identify the main factors influencing material behavior. Understanding these parameters is crucial for designing materials with specific mechanical properties, enhancing their applicability in various industries. So consider the dataset given in the table and answer how do materialness, temperature, stress, and strain contribute to variations in material behavior? Our seventh application is robotics. In the field of robotics, we explore the relationships between joint angles, motor torque, robot velocity, and applied loads. Joint angles influence the range of motion, motor torque affects joint rotation, robot velocity influences movement speed, and applied loads impact structural stress. PCA will help us identify the main factors shaping robotic performance. Optimizing these parameters is crucial for designing robots with precise movements and high efficiency, enhancing their applicability in various industries. So consider the dataset given in the and answer: how do joint angles, motor torque, robot velocity, and applied loads contribute to variations in robotic performance? Our last application is energy systems. In energy systems, we explore the relationships between energy consumption, efficiency, temperature, and flow rates. Energy consumption influences overall system performance, efficiency affects energy conversion, temperature impacts system stability, and flow rates determine fluid dynamics. PCA will help us identify the main factors influencing energy system behavior. Optimizing these parameters is crucial for designing efficient energy systems, enhancing sustainability, and reducing environmental impact. So consider the dataset given in the answer: how do energy consumption, efficiency, temperature, and flow rates contribute to variations in energy system behavior? Thank you for joining me on this exploration of principal component analysis in various domains of mechanical engineering. I hope you found the insights valuable and applicable. If you have any thoughts, questions, or specific topics you'd like to see in future videos, please feel free to share them in the comment box below. Your feedback is immensely appreciated, and I look forward to hearing from each one of you. Stay curious, and don't forget to subscribe for more exciting content. Until next time, happy learning.